Now, this section poses huge problems for most students. This deals with the academic security models. These, in many cases, are formal mathematical proofs of security, how to implement security. And when I speak about security here, I'm talking about discretely confidentiality on some models and integrity on some other models. Generally speaking, these academic mathematical formal models don't deal with providing availability. So we're going to be looking again at these abstract mathematical formal models that help to define how you will satisfy different security objectives. So the first thing we're going to look at is the security model itself. Again, it's a formal mathematical summation of, if we had a specific security objective such as confidentiality, how would you implement your security so that confidentiality of information will be retained? We'll look at other models that deal with satisfying the security objective of integrity. And again, mathematically proven in many cases how you might implement your security so that integrity of information can remain high. So to implement these formal models, what we do is identify what the security needs are for a specific process or program or system, and then we take pieces and parts from each of these academic models and put them together in a hybrid fashion. Not necessarily using all the components from any one model. I'll take pieces as I need to satisfy a specific business objective. Remember, this is a business-driven certification. So I'll pull these pieces together in bits and pieces and implement them in my programming code or the operating system code, or even in hardware perhaps, to ensure that I've satisfied the specific security objectives that this particular process or system demands. Now, these models are based on a couple of foundational components. The first foundational component that these academic models deal with is the concept of the state machine. The state machine is, again, a mathematical model that says, or it recognizes, that many different things can happen. Programming is a very versatile process, and there's no telling what processes and programs will be created over the next 5 years or 50 years or 500 years. In other words, we could evolve into a state where we have many, perhaps even infinite possible worlds of state on any computer because of the evolution of how programming works. And the state machine further then says that in order for us to implement security in any manner on a system that is maintaining our valuable information assets, we have to ensure that the last two bullets here, that if a machine comes up in a secure state and all state transitions are secure, including devices and programs that fail, and if the machine can also shut down in a secure state, then the system will remain secure. So that says, power up securely, do whatever you have to do, even if it's fail, do that securely, and shut down securely. And what you have is a foundation for an operating system and applications that can remain secure. So to summarize again, the bottom bullet now, no matter what input, output, or processing tasks that take place, all states will remain secure. These are the fundamental concepts of the state machine. And again, these mathematical models enhance this state machine. We say we have this foundational concept of security no matter what happens. Now with that in mind, the machine itself, the computer and the operating system themselves will remain secure. Now I can build upon that. All right, let's add a user into this and some programs into this, and now we can start to implement this higher level of security once we have this foundational state machine below us. A second model that is considered foundational to the majority of these other academic models is the information flow model. And the very top bullet on this slide tells us that information must flow securely through a state machine. In other words, as it's transitioning from one state to another state, it will remain secure. See, the state machine said as we're at this state or that state, we'll be secure. What about the in-betweens? So these two work together to ensure that in this model, as the machine powers up and it's at a secure state, and then we start to manipulate the data, and at the end point of each of those manipulations it's secure, and information flow says, and even as we're manipulating that data, all the information will remain secure. Now we have, again, this foundation that we can build these higher level models, such as the Bell-LaPadula and the BIBA, which we'll be talking about shortly. So again, the two things to remember about the information flow model is information must flow securely through a state machine system, and we recognize that these transitions will be only four in nature. They will be input to output, input to the next system state, state to state, and state to output. Those are the only four ways that information can flow through a system. And as long as we can ensure that that flow is secure, and we perform that flow on a state machine, which defines the states are secure, we know that we have a secure system. And again, now we can implement higher level security mechanisms. So to take the information flow model a step further, it specifically identifies that if data can flow from object A to object B, this is defined as explicit flow, and we have implicit flow if data can flow from object A to object B and then can securely flow from B to object C. Now data has flowed from object A to object C in a secure manner. Again, this is called implicit flow as we get from A to C.